All right, let's talk about TeX. If you've ever read a scientific paper, or maybe a math textbook, and you've seen those perfectly crisp, beautiful equations, well, you've seen TeX at work. This is the story of the system that completely changed the game for technical and scientific publishing. And our story starts where so many great inventions do, with a moment of pure frustration. The genius computer scientist, Stanford professor Donald Knuth, was getting ready to publish the second volume of his life's work, The Art of Computer Programming. But when the proofs came back from the publisher, they were just bad. The beautiful, classic typography from the first edition was gone, replaced by something he found totally unacceptable. So what does a genius do when faced with a problem like this? Well, instead of just complaining, he decided to fix it himself. Not just for him, but for everyone, forever. So let's dive in. We're going to look at the revolution he kicked off, his really unique design philosophy, how tech actually works its magic, its evolution into the more famous LaTeX, its incredible legacy, and finally, why it's still so important today. You see, Knuth's problem wasn't just his problem. Back in the 70s, the publishing world was moving from old-school hot metal typesetting to a new digital method. And in that switch, a lot of the artistry and quality was just getting lost, especially when it came to complex mathematical formulas. So we built TeX. And let's be clear, TeX is not a word processor like Microsoft Word. It's a full-on typesetting system. You can think of it less like a simple typewriter and more like having a master printer, a true typographic expert, encoded into software, with one mission: to create a perfect page. And right from the very beginning, he had two crystal-clear goals. First, he wanted to make beautiful typography accessible to everyone, so any person could produce a document that looked professionally published. And second, and this is the really critical part, he wanted to build a system that was completely stable. So stable that a file you create today would produce the exact same result on any computer 10, 20, even 50 years from now. And that obsession with permanence, with building something to last forever, is what truly makes TeX so different. Knuth wasn't trying to build an app that would be obsolete in a few years. He was trying to create a timeless digital artifact, something as enduring as the mathematics it was designed to print. You can actually see this philosophy in the way it was developed. The first version came out in '78, but then a huge rewrite in 1982 introduced something called fixed-point arithmetic. Now that sounds technical, but what it meant was that TeX would get the exact same result on every single computer, no matter the hardware. By 1990, the core system was basically done. And since then, the version number has just been slowly adding the digits of pi, which is Knuth's way of saying, yeah, this is stable, this is complete. I mean, this quote just says it all. He has famously said that the absolute final change to TeX, which will only happen after he's gone, will be to set the version number to exactly pi. And at that point, any bugs that are still left, they just become features. Now that is commitment to stability. Okay, so how does it actually work? How does TeX take simple text and turn it into these gorgeous documents? Well, the magic is all about how it treats math and code. As a user, you're not clicking buttons or dragging symbols around. Instead, you just write in plain text, using a special language to describe the math. So you type out the logic of, say, the quadratic formula, and you're just focusing purely on the content, not on how it looks. And this is what you get. The text engine takes that code, it understands the mathematical structure, and it applies literally centuries of typographic knowledge to render it perfectly. The spacing, the size of the square root symbol, the alignment of the fraction, it's all handled for you automatically. And this isn't just random. TeX uses incredibly powerful algorithms. For math spacing, Knuth literally studied the most beautiful math books ever printed to codify the rules. For breaking paragraphs into lines, it doesn't just go one line at a time. It uses a total fit algorithm that looks at the entire paragraph at once to find the absolute best place to break every single line. So there are no awkward gaps. It's brilliant. Now, as powerful as the TeX engine is, it's also, very low level. It's almost like a programming language. And for most people, that's a bit much for writing a simple document. This is what led to the creation of its much more famous successor, LaTeX. So you can think of the whole ecosystem in 3 layers. At the very bottom, you have TeX. That's the raw, powerful engine. Sitting on top of that, you have LaTeX, which is really just a huge set of pre-written commands or macros that make it way easier to create documents. And then you have thousands of packages that add even more functionality. So with LaTeX, created by Leslie Lamport, you get simple commands like document class article or section introduction. You just focus on the structure of your document. This is a title, this is a section, this is a list, and LaTeX handles all the complex formatting for you using that powerful tech engine under the hood. And the creation of this whole ecosystem didn't just have a small impact. It became the invisible bedrock that almost all of modern scientific communication is built on. Today, if you're in fields like math, computer science, physics, engineering, TeX isn't just an option. It is the standard. It is the language that scientists and researchers use to communicate with each other with absolute clarity and precision. This stability was a total game changer for publishing. Big academic publishers adopted it because they knew a manuscript would look perfect every time. And this, in turn, is what made online archives like Archive possible. Suddenly, physicists could share their latest papers instantly, around the globe, in a high-quality format, which massively sped up the pace of science itself. So, I know what you might be thinking. In a world with Google Docs and all these modern word processors, why on earth should anyone care about a system that was designed in the 1970s? Well, it really comes down to a fundamental difference in philosophy. A normal word processor mixes your content and your formatting all together on the screen. TeX forces you to separate them. You focus on what you're writing and then you describe how it should look. And this separation gives you absolute control, much higher quality, and of course, that incredible stability. Your source files are just plain text, they'll never go out of date. Look, there's a learning curve, absolutely, but the payoff is immense. You get to produce documents that have the quality of a professionally published book. You know your work is future-proof. You get total control over every little detail. And because the files are just text, it's a dream for collaborating with modern tools like Git. Ultimately, TeX is about a different way of thinking about your work. It's about moving beyond just writing a document, and instead truly crafting it with precision, with beauty, and with an eye towards permanence. It asks you a simple question: are you ready to master your documents?